So today we're going to start looking at applications of integrals. The first one is sort of abstract still. It's about finding the area between curves. So we're going to start with some sort of a review of some basic things that we hopefully got from the last video on the introduction to integrals, which is just a basic area under a curve. So when we see a figure like this, we have a function and we have a and b, and we have the x-axis. We call this area down here the area under the curve. So we can call, this area the area under a certain function. I'm going to do area of y equals 1 over x. This is obviously not the graph of 1 over x, but this is just sort of an example. From a to b. So we say the area under the curve over the interval ab is the area given by the integral from a to b of f of x dx. So we say the integral from a to b of f of x dx. So I think I haven't emphasized enough that these numbers in here in the integral are called the limits of integration. And they arise from the beginning and end point of the area you're considering. All right, so we're going to do some examples. So first example, we're going to find the area under y equals 1 over x from 1 to e. I picked this one because this is one you did a Riemann sum for, and you might recall what that looks like. So here's the graph of 1 over x. Of course, it has a negative branch down here, but we're doing from 1 to e, so we're not going to look at that negative branch. So we're looking at from 1 to e, and we want to find this area right here. So we call that the area under y equals 1 over x from 1 to e, or over the interval 1 to e. So some people who made mistakes with the Riemann sum started their interval over here at 0. And interesting things happen since this is a vertical asymptote. We will learn to deal with this later. All right, but I will just say interesting things happen because this area in here seems like it should be infinite, doesn't it? Maybe it is, maybe it isn't. Calculus is weird. All right, so we will find out about that later. For now, we're going to restrict our attention. We're going to keep away from the asymptote. That's why this interval was 1 to e. And then I picked e because you get a sort of surprising result. So in order to get this area, we're just going to say that the area is equal to the integral from 1 to e of 1 over x dx, because that's our function, f of x equals 1 over x. So you can do this on your own if you're confident with these already. Pause the video and do it on your own, or you can just watch. Your choice. So we say we're going to change our integral to a bracket. The 1 over x, we need an antiderivative. The antiderivative of 1 over x is ln of absolute value of x, because the derivative of ln of x is 1 over x. But we've discussed how the derivative of the ln of absolute value of x is also 1 over x. So we need this absolute value because it could pick up any negative values that we might have. Of course, we don't have any x's over here on the negative side for this figure. So in this case, the absolute value is unimportant. However, make sure you have it because one day it will be. All right, so, notationally pay attention to what's going on. I have an integral. I have my limits of integration here, the upper limit and the lower limit. I have my dx. As soon as I insert an antiderivative, the integral sign changes to the evaluation sign. The dx goes away because that was part of the integral sign. The evaluation brackets show up, and the limits of integration go over here. And there are different ways to write this, but this is the most common way. All right, so then what this means is that I'm going to plug in the upper limit and have ln of the absolute value of e, and then minus, I plug in the lower limit. So remember that there's always a minus in between. That's from that fundamental theorem of calculus, that the integral from a to b of f of x dx is equal to f of b minus f of a, where capital F is an antiderivative of small f. All right, so there's this, and then I can just figure these out. Well, I don't need the absolute value on a positive number, so it's ln e minus ln 1, and since you know your logs, you know this is 1 minus 0, which is 1. All right, so when I checked your Riemann sum answers, I just checked to see, is the answer you got close to 1? And, then if it wasn't, then I would know you did something wrong. So because the true area is 1, which is really surprising. All right, it's the same as a square with side 1. That's what the area is. Okay, now the next thing we have to look out for is you can have functions that, right, what made this area computation easy is that the function stays above the x-axis. So we can use this sort of simple definition of the area. But you can also have functions that dip below the x-axis. And then strange things happen because you know how the whole basis of the integral is that you have these rectangles and their height is f of x sub I, and you use a sub I equals f of x sub I delta x. All right, you're using that to calculate the areas, and the integral does that and takes a limit as n approaches infinity. However, down here, the f of x sub i's are negative. So if the f of x sub I is negative and the delta x is still positive, the a sub i's are all going to come out negative in here. So that means that as far as the integral is concerned, the integrals can represent this is a positive area and this is a negative area. So, you have to sort of wrestle conceptually with what that means. In simple cases where we're just looking for the area between the x-axis and the curve, often we will say total area between the x-axis and the curve to emphasize that I want to take just the positive parts. Then what I do is I just take the part where the function goes below the x-axis and I put a negative sign in front of that integral. So that essentially takes this part of the function and flips it up and then does a positive area. That's essentially what it does there, because that's going to be the graph of negative f of x. So then that you're going to do, but you have to be aware of where the function crosses the x-axis so that you can split the integral into the positive part and the negative part. The integral from a to b of f of x dx minus the integral from b to c of f of x dx, right? You're putting a minus here, but this integral is going to be negative, so you're actually making it come out positive. All right, you're making this term come out positive by putting a negative here. All right. You can also say, for example, that sometimes we want that negative value for this part of the area, because maybe this part is representing something like maybe the function is not representing area. Maybe it's representing something like work or thermal energy or something like that, a quantity that can go positive or negative. And then we would want to know that sometimes let's say this is like an exothermic reaction, is producing energy. This is an endothermic reaction, it's absorbing energy. And then at the end, we want to know what's the total change in energy. So we want to count the part below the x-axis as negative. So those are types of applications that can occur. We're not doing that right now, but we're definitely headed there. And then in that case, you can understand that the integral from a to c, is the area above the axis minus the area below the axis. Right? So in general, that integral, you're going to have to subtract out parts that are below the x-axis. And so just keep your eye on that because it's going to come into play later. So the next thing I want to do is do an example of a function that does this. We're going to find the area between the x-axis and the curve. I could emphasize the positivity of this by saying the total area. It's not necessary. It just helps clarify. Find the total area between the x-axis and the curve y equals x squared minus 3x plus 2 over 0, 2. You need to start by finding where is this function above the axis and where is this function below the axis on this interval. So you really need to start by sketching a graph of the function. All right, so I'm going to recommend you go ahead and start this, and I'm going to break and go to the next video and solve it.